Have you ever really stopped to think about how an AI like ChatGPT or BERT actually reads what you type? You hit enter and you get an answer, but what happens in between? Well, it's not magic, not at all. It's a fascinating process. And today, we're going to pull back the curtain on the very first and maybe the most crucial step: how AI makes sense of our messy human language. All right, so here's the game plan for this explainer. First, we're going to look at the whole tokenization pipeline from a bird's eye view. Then we'll zoom in on how the text gets all cleaned up. After that, we'll see how the very first splits are made. And finally, we'll get to the really cool part, the master algorithms that are the secret sauce behind it all. All right, let's kick things off with the big picture, the tokenization pipeline. Before we can get into the nitty-gritty of how it works, we really need to understand the why. What's the fundamental problem that this whole process is trying to solve? Think about it. Computers, at their very core, speak one language and one language only: numbers. They don't get words, they don't get your clever sarcasm, and they definitely don't get poetry. So we've got this huge translation problem, right? How do we take our messy, beautiful human language and turn it into a string of cold, hard numbers that an AI can actually crunch? Well, that's where this whole process called tokenization comes in. It's the bridge. But here's the thing, tokenization isn't just a single on-off switch. It's really more like a factory assembly line with a few key stages. First up, you've got normalization. Think of this as the cleaning station. Then the text moves on to pre-tokenization, where we make the first rough cuts. And finally, it hits the main event, subword tokenization. This is the really smart part, where special algorithms get to work building the AI's actual vocabulary. Okay, so let's start right at the beginning of that assembly line. Step 1, normalization. This is all about taking that raw, messy text and getting it ready for the real work ahead. You can really think of normalization as the mise en place for AI. Like when a chef gets all their ingredients prepped, chopped, measured, organized, before they even think about turning on the stove. That's what's happening here. We're getting rid of annoying extra spaces, we're making everything lowercase so the model doesn't get confused between the and the, and we're stripping out things like accents. The whole goal is just to create a super clean, super consistent starting point. And here's a perfect, simple example of what that looks like. So on the left, you've got the raw input with its fancy accents and exclamation points. Now, a model like BERT, using what's called an uncased tokenizer, just runs this through its normalization process. And poof, what comes out the other side is what you see on the right. Everything's lowercase, the accents are gone. It seems almost trivial, right? But this step is an absolutely critical foundation for everything that comes next. All right, so our text is all squeaky clean. Now it's time to move to the next station on the line and make the first cuts. This is called the pre-tokenization step. And this is where things start to get really interesting, because we start to see the unique personalities of different AI models shine through. So let's kick things off with BERT. Its approach is pretty straightforward, kind of what you'd expect. It just splits the sentence based on spaces and on punctuation. So the phrase "how are you" gets chopped up into 4 distinct pieces: how, are, you, and the question mark. And you'll notice that double space we had in there, BERT just ignores it. It's gone. Okay, now check this out. GPT-2 takes a totally different route. It also splits on spaces and punctuation, but here's the twist. Look closely. It actually keeps the spaces. It replaces them with that special G symbol. Why do that? Well, it means the model can perfectly reconstruct the original sentence, spaces and all. And see that extra G token floating in there? That's because, unlike BERT, GPT-2 did not ignore that double space. It kept it. And just to show you how different these approaches can be, let's look at T5. Its tokenizer is built on an algorithm called sentence piece, and it has its own unique style. It actually sticks a little underscore character at the start of a word to show that there was a space before it. But here's the biggest difference of all. It only splits on spaces, not punctuation. So that you, at this stage, it stays together as one single piece. So there you have it. 3 major models, 3 completely different ways of making the first cut. Okay, so those first cuts are made, but that's really just setting the stage. Now we get to the main event, the real heart of the operation. We're talking about the powerful subword algorithms that take these little pieces and intelligently build the final, super efficient vocabulary that the AI is actually going to use. Now, before we jump into comparing the big 3 algorithms, let's take a quick second to talk more about sentence piece, the one T5 uses. Its genius is that it's language agnostic. It treats everything as just a sequence of characters, even spaces. The big win here is that it makes the whole process completely reversible. You can always get your exact original text back, which isn't always true for others. And this is a total game changer for languages like Chinese or Japanese, where you don't even have spaces between words to begin with. Okay, this table right here is the key to understanding the three master algorithms. Let's just walk through it. First, look at how they're trained. You've got BPE, which GPT-2 uses, and WordPiece, which BERT uses. They're both what you'd call bottom-up. They start with a pile of individual characters and then learn, over and over, to merge the most common pairs together. It's like building with Legos. Unigram, which T5 uses, is the complete opposite. It's top-down. It starts with a ginormous vocabulary and then learns which pieces it can safely throw away to be more efficient. It's more like a sculptor, chipping away at a block of marble. And that basic difference in philosophy changes everything. When it's time to actually read new text, BPE just follows its simple merge rules. WordPiece is a little bit smarter. It merges pairs that have the highest probability of being a real subword. And then there's Unigram, the sculpture. It looks at a new word and figures out all the possible ways it could be split, and then it picks the one that's statistically the most likely. So you've got this fundamental tension, building up versus trimming down. And that's really a core distinction in how these AIs learn to see language. So when you put it all together, it's pretty clear, right? From the very first step, from that initial cleanup, different AI models like BERT, GPT, and T5, they literally see and process our words in fundamentally different ways. And that leaves us with a really big, fascinating question to chew on. If every AI model reads text differently, does that also mean that they understand it differently too?